Hi, this is Sundar. Welcome to Lecture 2, Materials Overview of the Design to Manufacture Digital Tools course. Here we will look at how to select the appropriate material for a situation called for by design from a whole world of nearly 200,000 different kinds of materials, which is ever growing with new materials research. Metals, ceramics, natural materials, glasses, polymers, composites, and foams, and many combinations of all of these. If you look at the design process that we considered in the opening lecture, you had a market pull for a new product, and you combine that with a problem statement of how we are going to address that market need. You go through an entire process that results in a new product that is being specified. Initially, in the design stages, it looks at things like, will it work? And then what might it look like? But before you're done, you have to look at what is it going to be made of, which is the material selection, which is part of module 1. How is it going to be made as a product? So the process, we'll look at that during module 4. And then, will it work well compared to alternatives? Will it be cheaper than other alternatives, right? So all these considerations get put in place. For example, with this particular example, here is a heat sink for microelectronic applications. We have to look at selecting a suitable material for this application and then decide on how we create a material choice through specifying what are some operating constraints and how do we optimize through various choices to find the best alternative. So what are likely to be design constraints for this application? Can you think of it? Some aspects are, it should be an electrical insulator, otherwise it will short out this whole set of electrical circuits. It should conduct heat, so thermal conductivity. There should be fewer thermal stresses, so the coefficient of thermal expansion, CTE, should be matched to the chips that are mounted on top of the heat sink. And then operating temperature, right? So it's going to get hot, and so it should be able to avoid getting degraded or losing shape during that time, and that for that temperature, which might be a maximum temperature. These are referred to as constraints that the design calls for. Having selected some alternatives, then we can go through a design objective of making something as cheap as possible or as light as possible. In order to go through this, we need to have data. What are the different attributes of materials? Which of them are relevant to this particular design situation? Then you need data on how to convert that material to a shape that is desired. And then a report overall, right, that documents what the recommendations are. In terms of material attributes, you'll have to look at a number of different properties, including general properties such as density and price, the modular strength, durability, so mechanical properties, and a lot more, in addition to the thermal properties that we looked at and the electrical properties. Given that you have over 200,000 options and dozens of properties for each option, to be able to filter through this requires digital tools that can compare, screen through options, prioritize based on a ranking what are the options of relevance, and finally make some recommendations. The constraints of the design are screened, and based on the data of properties, you create a ranking of materials. The objectives are then put together based on a free variable, and then a documentation is created. From that, we begin to get a final selection. So you can see that compared to other kinds of problems that you might have solved in a design situation, you typically have a number of different open-ended options or solutions from which you have to use a judgment. Let's look into greater detail at this application. You have these chips over here, they get hot. When in a very small volume, they have a lot of current density. This heat has to be removed to prevent damage to the material. This type of an application is growing in importance now with electric vehicles, and you also have autonomous vehicles that are combined with all the different sensors and that enable for driverless options. In terms of a design constraint, let's say, typically these things become hot enough to reach a temperature of around 200 degrees centigrade or more, and so we need to keep it below that so that degradation doesn't happen. And there to be electrical insulators as well. Okay, so these are the design constraints. What that means is we'll have to put down some numbers. Maximum service temperature should be below 200 degrees centigrade. It should be an electrical insulator. It should be a thermal conductivity. So what are those numbers? How do we look them up? And given that there are multiple constraints, how do we combine through all those different competing alternatives? In order to do that, we will work with a platform, as we will introduce during Module 2, which is a CES EduPack. That you go through the materials universe, and you can either plot them or you can apply some kinds of limits in addition to plotting them. Right? So the limit stage is based on what are some controlling design criteria in terms of thermal properties and electrical properties. At the first stage, the selection stage, here, if you decide that we want to look at thermal conductivity as a property, for all the different material classes, thermal conductivity is provided over this type of a range. Right? So these are called bar charts. And you can see that for families of materials, typically these properties fall within a specified range. Which are the most suitable for high thermal conductivity? It turns out it's a combination of ceramics and metals that will fall within that category. So if you want to maximize thermal conductivity, these will go away. If in addition, you want to limit it by addressing the fact that you want a thermal conductivity over a certain number, a service temperature over a certain number, or below a certain number, and if you want it to be an electrical insulator, then you get rid of, for instance, the glasses, the polymers based on this constraint, and you get rid of metals based on this constraint. So what you're left with are some highly conducting ceramics, aluminum nitride, alumina, silicon nitride as materials that work best for heat sinks for these kinds of demanding design constraints.